Okay. All right, guys. So I found out something about the sound. I don't know. The sound right now is okay. It's like everything is good so far. Yep. All right. I think I found out what's the problem. There was like an auto volume or something. So like the Zoom will just adjusting the level of sound automatically due to the environment or whatever. So every time that I had some changes going on with the sound, or maybe with the sound effect that I use, or I don't know, it probably just changes the level automatically. So I think I turned it off. So you guys just notice if things sort of go smoother, right? Once I turn this option, sort of like disable this automatic volume adjustment on and on. Okay. Already. Okay. So first, let me answer your question about the submission. Why the homework submission has only like just partial problems that get you to fill out the form is because I don't need all of the answers, right? Because we already discussed about this, that all I needed from you was just at least you have a chance to try. I mean, not just only try, but you go through the problems and sort of, try to understand the questions and try to solve it. And I don't too serious about the correctness of the final answer. So I think that's why. Okay, so just sort of like an evidence that you have already looked at the homework set. I think that's all I need. All right, and I picked just a couple of problems that seems like it's gonna be like crucial to exam preparation. So that's why there are only like maybe number one in this case and number six in homework number one submission. Okay, sounds good. All right, so I mean you don't have to punch in. Okay, is it cold in Wisconsin? Who's from Wisconsin here? What's going on? What did I miss? Oh, okay. Whoa. All right. Wow. Oh, yeah. I went through Wisconsin, correct. Yeah, but not at the moment. So I think it's fine. And I think it's cold regularly. So, yeah. So I haven't checked the weather back then. I mean, right now, what's up? Yeah, but it's always cold. All right. That's why I remember vividly that negative 40 Celsius is the same thing as negative 40 Fahrenheit. That was like, I think first year that I went there, it was like I mean, it's one of the coldest day in the past, maybe like decades or something. I mean, it's not like super cold, but at least temperatures went down and almost touched the all-time low or something. But it's not there. It's not negative 40, but it's somewhere like negative 30 or something. Yeah, that's why I just sort of like remember this negative 40 very well. All right, guys. So yeah, that was fun time. Okay, cool. All right, so guys, what I have for you today is going to be, it's like we're going to bring them all together. Okay, everything that we have learned since the beginning. We did like what it means by temperature. We brought you to understand heat just to make sure that it's energy transferred. And we sort of like calculate this and that about heat, a little bit about heat flow, calorimetry, and everything. And then we just say, okay, heat flow is the energy transfer. It behaves just like work in mechanics. Mechanics has the work as the energy transfer as well. So you can combine heat and work and put them all in thermal, situation, and then we have thermodynamics. So what we learned overall right now is everything has to follow conservation of energy, and that gave us first law of thermodynamics. Okay, so that's what we did pretty much. So I can put like a quick recap of, okay, let me slide back here. Yeah, here you go. So the main characters that we are looking at, there are three characters. Okay, the delta U. Okay, we're here, good. All right, that's just the change of the energy. So you think of it as like the amount of money in your pocket. All right. So if you have any transaction, it's going to change the money in your pocket. So there are two ways that you can bring the money in and out of your pocket. First, it could be through heat. Okay, and we agree that if the heat flow into your system, your money will grow. That's a positive change. If the heat leaves the system, that will give you a negative change to your money in the pockets. All right. And then your money is internal energy. Another way that you can do is through work. Okay. So if the gas perform work, it's just like you spend your money, and that will give a negative impact onto the change of your money, internal energy. And on the other hand, if somebody works on the system, so this means somebody just sort of like throw money at you, then you have an increase in energy in your pocket. All right. But because somebody throwing money to you, you're not working anything, you're doing a negative work. And that's give you a positive change in your internal energy. All right. So I hope this analogy helps a little bit. All right. And this analogy will emphasize on the key that the internal energy itself, just only the U, that is the amount of energy that's contained in the body. But in this first law of thermodynamics here, it's the delta U. Okay, it's the change of the internal energy. And that's why on the right-hand side of this equation is just a transaction. It's going to be some transfer. Okay, cool. All right, so I hope that we give you the overall pictures of the first law of thermodynamics. All right, so let's dive in, guys. So what we're going to do is we're going to look at the most famous or maybe the most popular thermodynamics processes, and we see from what we have already learned, what can we say is about those processes. All right, there are 4 of them that I'm going to introduce to you. First is, I would say the easiest one I say, is the isochoric process, or it's a constant volume process, or isovolumetric process, or whatever. The key is volume is constant. Okay. So it's easy. It's going to be a vertical line in a PV diagram, the one that does not change the volume. Okay. So, okay, there's a question coming. If pressure is directly proportional to the energy, right? Well, when we say something like this, it's going to be tough now, because when you say you increase the pressure, how can I say? Okay, I'll try to give you an example. Okay, think of it this way, guys. I think that's a very good question, because I think many of you still sort of like have that kind of like the feeling or intuitive thought that, okay, if you have higher pressure, mean higher energy, right? So I'm trying to have a counter example a little bit. So remember, guys, last time we were talking about the PV diagram, right? Okay. And we said every time you have a PV diagram, you can imagine you can visualize an imaginary, doesn't have to be imaginary, it's just over there. You can imagine that you have like a faint isotherm. Remember that? Yeah. Yeah. Cool. Yeah. There you go. All right. And that means the higher isotherm mean the higher temperature. And now from what we did last time, we sort of understand that if you jump from lower isotherm to a higher one, that means you are up your temperature. So that means your internal energy will be changed in the positive direction. You guys with me so far? Okay. Now, let me standing in the middle of these 3 lines right there. Okay. And your question is this: if pressure is proportional to the energy, what does it mean? It means if you increase the energy, increase your pressure means higher energy. However, if you look at this one, use PV diagram to help. You can change your pressure. It means you're going up along the y-axis. You guys with me? Okay. So you want to change your pressure up. So let me draw a horizontal line right here. So as long as you move your red dots upward along the y-axis, it means you increase your temperature. I'm sorry, my bad. If you up your red dots above that green dash line, you're going up along the y-axis. That means you increase your pressure. Yes, with me. Now you have multiple ways that you can increase your pressure. If you go directly up, that is fine. It seems like you're jumping from lower isotherm to a higher one. So your temperature increases, and that means your energy will increase along with it. So far, so good. But then if you notice, there are multiple, like millions of ways that you can increase your pressure. If I increase pressure this way, along this line right here, what do you think? Yes, with me? You can see that the red dot goes to the blue dot at the end over here. It increases its pressure. However, you can see that I'm jumping from a higher isotherm to a lower lying isotherm. In this case, your internal energy will reduce. See, there's so many ways that's possible now. Okay, guys. Or I can even have the third one if I start from the red and I just go straight here, but then I end up on the same isotherm. See, I'm increasing my pressure, but I'm not changing the temperature. I land on the same isotherm. So my internal energy does not change. So they are all possible. Changing the pressure does not directly tell you what happens to the energy. All right. You have to know exactly what happens to the gas through some path, some line, and some processes that can be written or can be drawn in the PV diagram for you to be able to determine what is actually happens to the energy of the system. Sounds good?
Okay.
Okay, this is like a long answer, but I hope it's clear things up a little bit. All right, does that help? Okay. All right. Okay. So I think this is a very good question because some of you feel like it's kind of like, okay, it's just like the question that we had with the temperature. Like I'm asking you like, hey guys, if I increase the temperature, it means like the gas has to rise in temperature, yes or no? And then once you understand that there is thermodynamics going on here, you have to ask me back because the information is still incomplete. You have to know, Ajahn, does the gas expand? If the gas expands as well and it expands so much, it could be that when you warm up the gas, it turns out gas might get cooler, something like that. Okay, so there are three characters, three main characters that we have to worry about. It's a change in the U, the Q, and the W. So you always have to know all of them first before you can decide what's going on with the system. Okay, all right, let's dive back into this. So start from the first one. So over here, the volume does not change. So when the volume does not change, then that's easy. The W is definitely going to be zero, no volume change, no work done. And the first law of thermodynamics will just read change in internal energy is just Q, and you done. All right, we're gonna go deeper in detail, all right, but I'll this give you an overview of what are things that we are about to dive into the detail. There are four processes here. Number two, we have a constant pressure process. So it's an isobaric process. It's going to be just a horizontal line in a PV diagram, okay, constant pressure. Good thing about this one is, okay, the volume, definitely you can see the change in the volume. If you follow this arrow over here, it means the system is expanding, but that's all right. The area under the curve is so easy to calculate. It's just the area of the rectangular region right here. So it's just the height times the width, and then you're going to get the W right there. Okay, cool. So W can be calculated. And once you have that, your first law of thermodynamics will contain all three terms right there. Okay, you should have heat and you should have the work done. And these two just get into your first law of thermodynamics all together. Okay, next, isothermal. Okay, in this case, it's a constant temperature. That's why we name it isotherm, right? Therm is like, temperature. Iso is mean constant. So it's a constant temperature process. So in this case, once again, you can just recall that, hey, every time I see PV diagram, I would like to imagine that there is a sort of like a constant temperature line all the time here. Right there, yeah, right, something like that. So if you are fixed in temperature, it means this process must be riding on a single isotherm. You cannot jump out of it. It's stuck in there, right? So that's why the process that has an isotherm, a constant temperature has to be right on, right there. Okay, cool. So the good thing about this one is what? Ajahn, no temperature change. There will be no internal energy change as well. All right, but okay, W is still all right. Well done. I can still figure out the W, area under the curve. Well, we'll do that. But once you're done with that, then the first law of thermodynamics will read Q equal to, okay, let me write on top here. Q equal to W. You guys with me? Because delta U is gone, I can just move W to the other side, and then you say, whatever the W that you calculated from the area under the curve, it will be exactly equal to the heat that is flowing. Isn't that cool?
Okay.
So you start to get the feeling of what is going on now. Yeah. And the last one, it's going to be the one that's okay, because we already played with all of the variables here. The only thing left for you to play around with is the heat. So the fourth one is called adiabatic process. And this one, you do not allow any heat to exchange whatsoever. Okay. So when you don't have any heat exchange, what do you get? Q equal to 0. So when Q equal to 0, the first law of thermodynamics will read delta U equal to negative W. All right. So that is an pretty much like the grand view of what we are about to, at least go into a little bit more detail of how to extract even more information out of this. Okay.
Okay.
As you can see, there's so many information sort of floating around right here. And that's why, all right, and just to be honest, back in the day of like high school physics, thermodynamics is the one that I hate the most. It's like, what? The limit of studying this topic is pretty like approaching biology, something like that. So many things to memorize at the time. Okay. But after, look into details, oh, it's not that bad. Okay. Even though it's still information is still a lot, but it doesn't mean like you just have to memorize anything. If you understand the principle, no, it's still all right. Thank you. Too bad. Not too bad. Okay, guys, let's go through each of those 4 processes one by one, shall we? Okay, start from the easiest one, isochoric or isovolumetric process. Okay, this one is easy. We just said the W is 0. So your first law of thermodynamics just reduced to the change of the internal energy. It's just equal to heat in this process. And this one is good because this is going to be the easiest one that you have seen before, like this, right? Remember that we discussed this and we just said about, oh, whoa, 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 wrong one. Sorry. Oh, I don't have that. Oh, okay, maybe my bad. I thought I had that figure here. It's not. Okay, that's fine. Sorry, my bad, my bad. Okay, so what I have over here is just the common scenario that we used to so much. This is the case when the volume is fixed. Okay, and when the volume is fixed, there's no work done. So if I ask you again, well, hey guys, now I have a condition that the volume will not change. What happened when I warm up the gas? Yeah, this is the one that you can say about Ajahn, temperature will rise because the W is not in the picture. So whatever the heat that you transfer to the gas will definitely go into the change of the internal energy. And definitely internal energy will be a positive change if you throw in some energy to it. And that gives you the positive change in the temperature as well. You guys with me?
Okay.
All right. So this is a common case that you familiar with. You warm up the gas get hotter. This is it. All right. This come along with the condition that you do not allow gas to expand. All right. What next? Because you knew from equation of state is an ideal gas, and from we already concluded this from kinetic theory of gas and everything, you can calculate the internal energy of a monatomic ideal gas to be 3/2 nRT, correct? Okay, this one,
Okay.
no problem. So what you're seeing over here is the delta U is going to be 3/2 nR delta T all the time. That's okay, that's for sure. Okay, temperature change means internal energy change. We don't have any ambiguity there. When you talk about monatomic gas, this is always the case. Energy depends on the temperature. You know the temperature, you know the internal energy. Okay. Now, this one is just equal to Q now. Whoa. And let me rearrange this one expression in this form. I put N in the front. I sort of grab 3/2 R, pull them together, and then put the delta T toward the ends. What do you see? No, you don't need that. Saturday morning then. Don't be too loud. Okay, what do you see? Q equal to N with the bracket 3 half R and then followed by the delta T. Any sort of like, something cool that you have seen before? All right, I'm just gonna tell you right away. Remember this back in the calorimetry, MC delta T? Yeah. But then when we are looking at the gas, we're not gonna ask you about the mass of the gas. It's kind of like, you don't have like a scale or something to weigh the gas. Usually don't talk about that. But the structure of the equation looks similar, almost exactly the same actually. So you have the amount, you have the constant, and then you have the temperature change. Yeah. So actually the equation that you're having right now is the same kind as the equation that tells you about the heat capacity. Okay.
Okay.
So what I can now summarize for you guys is this. So this bracket right here can be interpreted just like the C back in the day of the specific heat. So what you see for 3 half R is going to have the same meaning, which is going to be the heat capacity. But what we had before, it was the heat capacity per kilogram. It's the mass, it's kilogram. But what you have over here is it's the mole. So that is fine. But interpretation stays the same. So now what you can say is that extra terms right there, 3 half R, can be thought of as the heat capacity per mole. So that's why we're going to name this a molar. Molar mean per mole, sort of like, and then heat capacity. But because we derive this equation from the constant volume process, so we're going to say that at constant volume, and we're going to have a subscript V for that. So now I can rearrange this equation to look like this. Very nice. So now delta U equal to Q equal to NC sub V delta T. All right. And we're going to stick with the monatomic ideal gas. If you have like, diatomic or triatomic, this C sub V will change, depends on the shape of everything. But what you can now, I hope, you can relate just a little bit. The reason that the number 3 shows up right here is because remember that we talked about when you have just like a single particle in the universe. Remember that? Yeah. That was back in the day that we sort of first met, I think, last week. And then I said, hey, I light the fire, give it some energy. What happens to this? And then you just told me that, okay, Ajahn, it's probably, not probably now, it's going to move. It's going to get some velocity. So it means it's going to have kinetic energy. But then if you look at this one, because this can travel in 3 directions, it's an x-axis, y-axis, and the z-axis. So that means you're going to have 3 components of the velocity, right? V sub x, V sub y, and V sub z. That's 3 dimension there. It's number 3 right there. And if you sort of like, remember vaguely, you might have heard of this word right here is the degree of freedom right there.
Okay.
Cool. So actually, if we spend time talking about the kinetic theory of gas, each degree of freedom will have the ability to store energy. Yeah, think of it that way, because this is the heat capacity, right? Ability to store energy. So each degree of freedom can contribute to the capacity of 1 half R. Isn't that amazing? Per mole. Isn't that nice? Okay, so, but now because you have a single particle monatomic gas, and because you have 3 degrees of freedom, because it can travel in 3 dimensions, so you have 3 times of that 1 half R. So that's why it's 3 half R. Okay, so no doubt, if you're talking about the more complex molecules, then there will be more degree of freedom. It not only that it can move, it can vibrate, it can bend, it can oscillate, all this stuff, then this number will grow. Depends on the complexity of the molecules. All right, sounds cool? All right, but at least this will give you some, connections between the number 3 that you see here and the specific heat per mole that we are talking about. All right, and some of you probably wondering, well, Dan, why do we have to define this kind of thing? It will become clear in a little bit later, but The thing that at least we can sort of like take advantage of is once you have a constant volume process like this equation will lead you directly to the heat flow within this process. So that's kind of
Okay.
nice. It's kind of nice. Okay. So if you say, okay, I can still not clear, why is this nice? Look at the next one. What about isobaric, guys? Well, okay, John, this one is still okay, easy to do because one thing that we know right away is this gas perform work. If you look at the process that going from left to right, so the volume increases, you can figure out the area under the curve, and that is going to be your work done, correct? Okay, let me do this together. W, let's start from the beginning, from the top. There you go. That's your definition of the work done by the system. Okay, just I want you to emphasize this again. We already agreed that from now on, the W is the W of the system. Okay, in this case, P is a constant. That's nice. I can pull it out from the integral. So the integral of dV is just V. And then you just use V sub I and V sub F to be your limit of integration. So at the end, the work done from here is just going to be PV final minus V initial, correct? Looks good. So far, so good.
Okay.
All right. And once again, just want to emphasize another point that if you follow this exact order of calculation, your mathematics over here will take care of the final sign of the work done for you. That means for in this case, you go from small volume to a bigger volume. Yeah, you can see that final volume minus initial volume will give you positive number because gas is expanding. Okay, but on the other hand, if you go backward, you go contracting the gas, this expression will give you negative number automatically. Okay, so that's kind of nice and cool. But anyway, for us at this point, all you're doing is just you take the width times the height, you get the area of that rectangular piece, and that is your W, correct? All right, now come back to our first law of thermodynamics, guys. So first law of thermodynamics say delta U equal to Q minus W. So far so good. Okay, let me do this together. So because the slide is already there for you. So first law of thermodynamics say delta U equal to Q minus W. I'm gonna write this equation until you get sick of this. All right. So what you have over here is delta U is equal to Q minus W right here, right? Is a P V final minus V initial, correct? All right. But now you already knew all the time that the delta U is always 3/2 NR delta T. No change. It's always the case. So what you have over here is, well, John, if I want to re-express this expression all in the form of the change in temperature, why not? Okay. So what I can do is I can pair this with the equation of state. So follow me here. So let me spread this thing in. PV final, PV initial, right? So what I'm getting is going to be negative PV final. And you can do plus if you want, but let me do it like this. There you go. PV initial there. Yeah. And then I recall the PV equal to nRT. I'm going to apply it right here. So I'm going to get Q minus PV final is going to be nRT final. You guys with me? PV initial there. And there are 2 points here, 2 ends points over there. It's going to be nRT initial, yeah? So that means the right-hand side look like nR delta T. Whoa, that's nice. So it means I can actually move this nR delta T and put it on the left-hand side that has 3/2 nR delta T waiting for me. So at the end, what I am arrived at is this expression here, Q equal to, you guys with me? Let me rearrange, N 5/2 R delta T. What do you see?
Okay.
Same form, just like before. It's like N molar specific heat C delta T. Same thing over here. So that's why what you're looking at is the same form as this one, Q equal to N C delta T. So that 5/2 R now is going to be the heat capacity again per mole, molar. But then you got this expression from constant pressure. So it's going to be at constant pressure. So let me put subscript P with that. And you are done. So that means in the constant pressure process, if you want to jump right into the heat flow during this process, you can use N5 half R delta T to calculate. Isn't that cool?
Okay.
Yeah, you probably like, what's so cool here, guys? It's like, what? All right, don't worry. I think things sort of like, getting, and it still look fancy to you. It's like, it's unclear, it's cloudy. Like today, it's like even raining at this point. All right, so it's cloudy. All right, it will be much more clearer when we, dive into some more exercises. Okay, but at least now you sort of like, okay, follow along, get a feeling of what is going on. All right. I can calculate the work done. I can calculate the heat flow. I can rearrange the heat flow to make it look like a, heat capacity like equation. All right. But the utility of this coming. All right. Coming.
Okay.
All right. Next, guy. The third process is an isothermal process. And here comes the extra calculus. With no extra charge, guys. All right. You're going to have a chance to try, practice some of your, calculus that you learned from calculus 1, maybe. That should be enough. Okay, here we go. Next one, isothermal process. All right, this is good because we already discussed that, okay, it must be the line that is riding on a single isotherm. Cool. And definitely delta U will be 0 because no temperature change, internal energy is constant. Delta U will go to 0. So that's nice. That term is gone. So your first law of thermodynamics look like this. The amount of heat flow during this process will be exactly equal to the work done by the system. Cool? How much? That is the question. Well done. That's easy. Just find the area under the curve. And that is still the same question. How much? If your gas is expanding, in this case, it's expanding from V sub I to V sub F, you know in your head that the work done is going to be positive for sure. Okay. And you know that from the first law of thermodynamics, the Q will be positive along with it. How much is the work done? How much or what is the area under this curve at this point? Start from the top. The W equal to PdV. Yeah, cool. All right, guys, keep going. How? In this case, how? P cannot be pulled out from this integral anymore because the pressure is not a constant, right? So you have to now do the integral. So the only way that you can do this is you have to turn P into a function of V. So you will be able to integrate using V as your integrating variable, correct? And then you say, okay, no problem because PV equal to nRT. So that means P is nRT over V. With me, guys?
Okay.
Substitute it in, everyone. nRT over V dV, starting from initial volume to the final volume. Next, keep going. N constant, R constant, T constant. So actually I can pull that nRT out. You are left with just the integral of 1 over V dV. What is the integral of 1 over V, guys? Very good. Log of V. And that's what you get. nRT log of V, starting from initial to the final. And that lead you to this final integral right there. And you are done.
Okay.
Okay, and this one definitely is going to be the same as the heat as well. So as you can see, the sign has already been taken care of automatically. Because if V2 is bigger than V1, you have log of the number that is larger than 1, the value of the log is positive. If V2 or V final is less than V1, which is V initial, then it means you have a log of the number that is less than 1, the value of the log is negative. See? Perfect. Okay, expanding, you get positive work. Contracting, you get negative work. And that is definitely equal to the heat flow during this process as well. Okay. And have you seen this process before? Answer is yes. Now I have the figure for you. It's right here. Remember this scenario that we discussed last time? The one that the gas is attached to the energy reservoir. So you are guaranteed that the temperature of the gas will not change. So with this, then okay, Ajahn, because the temperature of the gas cannot be changed, but the gas is expanding. Remember, the gas is growing, expanding, but it cannot change its temperature. It cannot change its internal energy. The only way that this is possible means there must be some heat flow into the gas. And the amount of Q that flow in is exactly equal to the W that the work is being done by the gas. And that is isothermal process that you saw before, constant temperature process. Is that cool? Alrighty. All right. So I hope that's sort of like the idea that, give you some connections between the Q, the W, and the W, on and on. First law of thermodynamics all along. Any questions so far? All right. If not, fourth one, guys. Last one. Here we go. Now, this one, I will challenge you a little bit. Okay. Because this one is like, okay, this is going to be the weirdest one. To me, the reason is because we're not going to have any specific expression or anything per se to describe the curve that has no heat exchange. All right. So adiabatic is the process that no heat transfer. So Q is 0. So the first law of thermodynamics will read Q minus W. You throw away the Q. That's it. So you get this expression, right? My question is this. What is going to be the shape of the curve that representing a diabetic process? Whew. What do you think? From the delta U equal to negative W, what should be the shape of the adiabatic process curve? What do you think? All right, this is sort of like crucial in understanding this. And I think this is nice to have this one as your final famous process to study. So what it says right here is, if the work done by the system is positive, you're definitely going to have the lower internal energy. Make sense? Because delta U is negative W. It's always, it happens like this, right? Because if the gas perform work, it means it has to spend the energy. Your money in the pocket must be lower because you're spending your energy, you're spending your money. So the level of money in your pocket must be negative change. I mean, must be lower. All right. So what should be the shape of this curve? Here we go. Follow me here. It's already sort of, showing you right here in this curve. But do you understand why the adiabatic process curve looks like this? What do you think? What is the relationship between the delta U equal to negative W and that orange curve right here? Okay, think carefully here. So imagine this. What they are showing you here is the contraction, right? They're compressing down the gas. You're starting from the initial volume. You're compressing the gas down. Okay, cool. So right now, if you look at the work done by the gas, is going to be a negative work done. Cool. W is negative, right? And when you plug it in here, I mean, you don't need to plug in per se, but what I'm saying over here is when the W has a negative value, it will give you a positive change in the U. Delta U is going to be positive, correct? But the delta U positive means the temperature will be increases as well as the W is positive. With me, guys? But the temperature increases mean it has to jump out from a lower lying isotherm to a higher lying isotherm. Yes. So use the same idea that we had before. So assume that you have isotherm here, one in the lower temperature, one higher. And let me sort of draw another one somewhere in between. If I can, let's squeeze it in here. So follow here. If I start from this point, red one, and gas get compressed, delta U must up by a bit. You guys with me? Because when gas get compressed, W is negative, delta U must be positive. So delta U positive means delta T must be positive a bit. So temperature must rise a bit. So it means if I go left along the V axis, the X axis, I have to go up. I have to jump to a higher isotherm. Bam, right there. And if I keep going left, I have to go higher in isotherm. Left higher, left higher isotherm, left higher isotherm, left higher isotherm, left higher isotherm, on and on. So until I reaches the end. So if I go left, at the end, I have to finish at a higher lying isotherm. This is the reason why the adiabatic curve look like this. It's going to be steeper than the isothermal curve. Cool?
Okay.
Yes. Kind of quiet, but I hope that you understand this. Yes. All right. So that's it. So that's the meaning of this one. It's just like, okay, from now on, whenever you see the adiabatic curve, the curve that representing this process will be steeper than just an isothermal line. But then you say, Bajan, it's like, it's just a qualitative understanding of this. How can you pinpoint all those points in that, or all those dots that you are sort of like, writing on that adiabatic curve? Well, yeah, all these points on the adiabatic process will have the following relationship, guys. And this is it. Let me put like a 3 stars right here. It turns out every point on this adiabatic curve will follow PV to the gamma equal to constant. So that means along this curve, P1 V1 or Pi Vi to the gamma must be equal to PF Vf to the gamma. Isn't that cool? All right. Isn't that nice? In addition to everything that has already been, worked out fine for the gas, PV equal to nRT, U equal to 3 half nRT, P1 V1 over T1 equal to V2 V2. Everything works just like before. But once you are dealing with adiabatic process, it has an additional restriction to those points, right? The point on adiabatic curve has to also follow this conditional relationship, right? This is an extra. It's like a top up relationship that you have to add on. What is the gamma? And here we go, guys.
Okay.
That is the reason why I have to introduce to you C sub P and C sub V is just because the gamma that you're going to use here in adiabatic curve is just the ratio between those two. All right. We're not going to prove this one because it probably take, another half a lecture or so. But anyway, the point is that is the one that you can take home with is whenever you have adiabatic process, PV to the gamma on that process stay fixed. And the gamma is just a ratio between C sub P and C sub V. And the good thing is if we just focusing on our monatomic atoms or monatomic ideal gas, C sub P is already fixed at 5 half R. C sub V is already fixed at 3 half R. So that means, well, so that means from now on, if you, for sort of like, focus on just a monatomic gas, it means gamma equal to 5/3 at all time. The answer is yes.
Okay.
It's a constant. And it doesn't matter what type of atoms you're talking about, as long as it's monatomic. So this is a nice thing about the structure of the universe, guys. I mean, it sounds grand or sounds crazy, but that's what it is. As long as you have a single piece of particle with no internal structure, I don't care if this is going to be like a helium atoms. I don't care if this is like a neon atoms. I don't care if this is like a single hydrogen atoms. I don't care. They're sharing the same property means once it gets some energy, bam, it can travel in 3 directions. See? So that's why the heat capacity per mole in monatomic ideal gas, it's going to be exactly the same, 3/2 R, no matter what type of gas you are looking at. With me, guys?
Okay.
Okay, so this will sort of, I kind of like this one because it shows you like this reveal the structure of the universe. You don't need to attach yourself with the type of the gas. Doesn't matter. As long as you treat this one as a single particle, the ability to carry along the energy will have exactly the same value. Okay. 3/2 R per mole. That's a molar specific heat. Okay. Oh, that's a quick question here. Why is C sub P is 5/2? C sub P 5/2 is because of this one. All right, we derive here. The reason that the C sub P is higher is because you used part of the energy that flow into the system to expand the gas. You guys with me? So if you think carefully of this one, the reason that this one has a higher heat capacity per mole, because you allow the gas to expand. You want to fix your pressure. Okay, because you want to fix your pressure, it means you think like, I am the gas, right? You guys, we are all gas, let's say. But then let's say, well, hey guys, there will be some heat flow into us. But the conditions for us is, hey, you guys, keep the temperature fixed. Well, Ajahn, how could that be? Well, okay, we have to expand. If we don't expand, then our temperature will rise. I mean, you know, and then we cannot keep our pressure, because if we cannot expand, then not only temperature will rise, but our pressure will rise. So let's expand to keep our pressure fixed. That means now we are going to perform some work. And to perform work, we need additional energy to push out the volume. That's why there's more energy flow into it. So from the perspective of how much energy you are storing, it's going to be higher than just a regular, you know, constant volume process. Does that help? Does that make sense? All right, maybe this is a long version of the answer. The short version is we saw that here from adiabatic process. Okay. All right. So we derived C sub P to be 5/2. Okay. Oh, that's, but why 5/2 and not 6? Oh, okay. Is yeah. Okay. One more time. The reason for that is because we here, we were looking at a monatomic gas. Okay. So it does not have any internal structure. So when it does not have any internal structure, the only way that this particle can utilize the energy is just travel 1/2 mv squared. Okay. And because that v square over here composes of 3-dimensional velocity, there's an x component of v, y components of v, and the z components of v. So each component, think of it like, okay, there's, you know, one way of storing your energy. So in this case, you have 3 ways that you can store the energy. So hence that number 3 right there. Okay, but the 1/2 R came from the kinetic theory of gas, that explaining if you have a gas for a mole, and if it has a one way of storing energy, you will get 1/2 R as your heat capacity per mole. All right, so just to give you a big contrast over here. So if I give you this diatomic molecule instead of monatomic here, okay? So if you look at this one, then what you have is going to be, okay, but Ajahn, definitely this thing can still move. So you get 3 ways that you can store energy. But because you, wait, maybe spring is too complicated. Sorry. Let me put diatomic, but still fixed, still fixed. No oscillation. Okay, otherwise then it was just too much. Okay, here we go. So let me give you like a diatomic. Here we go. Bam, right there. All right, like a dumbbell. So it's like a dumbbell shape here. So once I provide this with some energy, and just burn it just like before. So you say, well, Ajahn, look at the CM of this one. You can still travel. So you have 3 velocity components just like before, right? No change. But then because you have internal structure now, well, Ajahn, I can now rotate. Okay. And the rotation, all right, that you can do, you can rotate along this axis. You can rotate along this axis. And then you can probably rotate along this axis over here, right? But then because when you look at this one, and if you remember the problem back in the day of the moment of inertia, if you go along this axis over here, you are piercing through the center of all the masses here. So the moment of inertia seems to be 0 in this case, if you assume that the particle is super small. So over here, you can just sort of get rid of that degree of freedom because that degree of freedom doesn't exist pretty much. So you get 2 additional movements from this and this rotation. So if this is the case, so now you have 5 ways of storing your energy. So in this particular case, if you are looking at diatomic gas, C sub V will be 5½ R. And then use the same idea that you derive C sub P. The C sub P for the diatomic gas would be 7½ R. And I hope this explains where the 3, the 5, the 5, the 7, and on comes from. Does that sound reasonable enough? Okay. All right. So yes or no? Okay. All right. So that is a reason. Yes. All right. Cool. All right. But anyway, because to us, we're just going to stick with monatomic gas for simplicity. So our number is always going to be fixed. 3½ R for C sub V, 5½ R for C sub P. All right. But in the future, if you found out more complex atoms, more complex molecules, well, more complex atom, that doesn't make sense. More complex molecules, compound molecules on and on, the C sub V definitely going to have a bigger number. All right. But it's going to be fixed for one particular shape of the molecules anyway. Okay, cool. All right, guys, that give you a conclusion for this. And after the break, we'll dive into some, calculations and details. And I hope that will give you more insight into how this can be utilized. Okay. All right, guys, take 10 and then we'll see you after the break. Okay. So the rest of the lecture is we are going to look at examples now. All right. So we're going to sort of like, go through all these stuff and see how those things end. Don't worry, even though after today's lecture, it's still sort of like, oh, wait. My memory is low. Let me close down something. Sorry, guys. It's just, okay. All right. It's just, yeah, it's 8 gig is not enough nowadays. Too bad I cannot expand my memory anymore. It's like on board. Okay, guys. So let me know if there was any, there is any quality problems. It just have a pop-up window saying that the audio quality might be affected. Okay, but I closed down something here. Okay, guys. So what if after today's lecture you still sort of like, it's kind of like, okay, John is unclear, whatever, don't worry, we will do more and more and more next week as well, because this is the basic that we are going to use for, pretty much everything in thermodynamics. All right. So you're going to see, like, until you get sick of this. All right. But let's start from an easy one first. One mole of an ideal gas does 3,000 joules of work on the surroundings at its expense. Isothermally, now you have to pay attention to which process you are dealing with. At this point, it's a constant temperature process. And then you go to a final pressure of 1 atm, volume of 25 liter. It seems like we're going to have some unit conversion maybe, but that's at least easy to do. Determine the initial volume and the initial temperature of the gas. All right, guys, what do you think? Is it doable? Okay, first thing first, all right, if you want to sort of like, start from the top, isothermal means delta U equal to 0. First law of thermodynamics will be just reduced down to 0 equal to Q minus W, or Q equal to W. What's more, we have already derived this area under the curve calculation is going to be nRT log V final over V initial. Yeah, all right. Get back to this. Yeah, isothermal process. Cool. That's fine.
Okay.
So with that, then it means all you need to do is just, grab some informations and then just try to figure out the missing piece, the one that they ask. Okay, what's the question? It turns out that there is here, gas does 3,000 joules of work. So it means the W is going to be positive 3,000. Okay, good.
Okay.
Yeah. What else? It's expand isothermally to a final. So this means this is a final conditions over here. So at least now the final pressure is 1 atm. Let me write it down for you. And the final volume is 25 liter. There you go. All right. So what do they know? They want to know. Sorry. They want to know initial volume and the initial temperature of the gas. All right. So not bad. Any clue? A lot of clues at this point. W is just equal to Q. So this term is known. Okay, let me highlight the one that's already known. This one is good. W is good. That's fine. Okay, V final is right there. That's good. No problem. That's already known. They want to figure out the initial volume. So this is what they want to know. The V sub I right there. That's what they want to figure out. What else do we know? Oh, what about nRT? Do we know nRT? Well, no big deal. We can always use PV equal to nRT. Let me use different color here. So PV equal to nRT all the time. So actually you can replace this nRT with the PV, and it could be any PV. It could be PIVI or it could be PFVF because it's constant temperature process. Doesn't matter. But then when you look at this one, oh, PFVF is good. So what I can actually write, continue from that, is going to be PFVF log V final over V initial. You guys with me?
Okay.
And once we have that, let's try plugging in the numbers, the one that we know, 3,000 joule on the left, that's the W or the Q. Pressure, 1 atm. Now, you want to convert into an SI system, so you can look it up. It's approximately about 10 to the 5th Pascal per atmosphere. So it's just a units conversion here. The volume, no big deal, 25 liter. You can always turn this into a cubic meter by multiplying by 10 to the negative 3 cubic meter. All right, very good. All right, and then you follow by the log of the V final. But now in the V final and V initial, you might not need to convert any units anymore if you want to stick with the liter. So what I can do is just I put 25 liter here, and I just put the unknown V initial right there. The final answer will be in the units of liter, which is fine. Okay, so at least this one gives you an idea how to apply the known stuff about the isothermal process, which is good, no big deal, right?
Okay.
And second thing is just to show you, how to be careful with the unit conversion, which part of the equation that need to be converted, which part that is okay if you just, want to work in that particular unit all along. That's fine. Don't need to change. So far so good, yeah. All right, and then from here you can just and then you should be able to figure out what is the initial volume that the question asked you. All right, and once you have that, then what is the initial temperature of the gas? Well, it doesn't matter. The initial temperature or final temperature, they are at the same temperature. So question about temperature can already be answered using PV equal to nRT. It's no big deal. So let me sort of here, move it right here. So over here, if you want, so from, let me write it out for you. So from PV equal to nRT, so the temperature is just going to be PV over nR. And you can use either condition, is fine. You're going to be PIVI, or you can use PFVF, no big deal. Okay. And as you can see, the pressure final is known, final volume is known. It's the 1 mole of gas, N is 1. R is just a constant, so you should be able to calculate the temperature right away. Okay, and it's going to be T sub I or T sub F, doesn't matter. They're both at the same temperature. Done.
Okay.
Seems all right. Not too bad, I hope. Okay, even though it doesn't look nice and neat, my writing is kind of like all over the place, but I hope, well, you see how to fill up the information that you already known, and then try to figure out the unknown of the question. Okay, try the next one, and things will get better and better over time. Yeah, try again, guys. So the figure shows a PV diagram for an ideal gas in which its absolute temperature at B is 1/4 of its absolute temperature at A. All right, now we have a PV diagram with a process. A, what volume does this gas occupy at point B? Whoa. Let's start with the first question, guys. What do you think? Woo. This is annoying, but sort of like wake you up a bit. All right. First question is like not yet thermodynamics. It's just the equation of states. You want to compare between point A and point B. What can you do? Well, Dan, that's fine. P A V A over V A T A equal to P B V B over T B. Yeah,
Okay.
All right. Oh, that looks like D. Let me erase that. So it's just comparing between two scenarios. All right, which is fine. And the good thing about this one is from A to B is a constant pressure. So this P will just go away. So of course, the ratio between the volume and temperature is fixed. So you can see that now they said that the temperature at B, here we go, T at B is 1/4 of temperature at A. So now you know this. This is a known information. So from the look of this one, of course, well, Adan, the pressure must be down 1/4 as well. Make sense to you guys? Yeah, because the ratio between V and T stay fixed. So when the temperature is down 4 times, pressure must down 4 times as well. So you know right away, this point B is going to be at 0.125 liter. Cool. Okay.
Okay.
All right. And once again, I just want you to sort of like have this in your head at all time. Don't forget that every time we have PV diagram, we have like an isothermal line, it's not like you can have this in your imaginary, visualization or whatever, but this is what it is. So, going from A to B, you jumping from a higher lying isotherm down to a lower lying isotherm. So it means you can expect that the temperature drop 4 times, which makes sense. Perfect, right? That's the problems told you. And the pressure must go down along with it 4 times as well. Okay, very good. Part A is done. Good. Now part B. Get going. How many joules of work was done by or on? So it means they just want to know is the W is positive or negative. The gas in this process, was it done? Okay, I saw this already. It's redundant. I forgot to erase this one. Okay, guys, how can you figure out the amount of work done during a process? Well done. That's just an area under the curve. So go for it. And this one is just a constant pressure process. So the W is integral P dV, but P is constant. Now you have done this before. And then it's just the integral of dV is just P delta V. With me, guys? Cool. All right. And because the pressure is known, all right, let me put 1.5. Okay, let me just put ATM for now. We can do the conversion whenever we want. And V change, don't forget to take the final minus initial, right? It's a V final minus V initial. So it's going to be 0.125. That is your final volume. And then you subtract that with 0.5. And this is in the liter units. All right. We can take care of the units conversion whenever you like. But that's what it is. At least you get negative number, which makes sense because you're compressing the gas from A to B. So the W is supposed to be a negative number. And you are done for the part B. Okay, so when you say, okay, Ajahn, I can see it's a negative one. So the work was done on. So there must be something else from the external, environment or whatever, person, experimenter, whoever, compressing down the gas. Okay. Okay, part C. Did the internal energy of the gas increase or decrease from A to B? Oh, this is easy to answer. Can you guys tell me right away? Internal energy of the gas increase or decrease? What do you think? Increase? Okay. Anybody else want to try? How can you tell it's decrease or increase? Internal energy is a U, right? U, delta U. So the U can be calculated from the T, right? That's the temperature changes or not. Going from A to B, you're jumping from higher lying isotherm to a lower one. Now you see where am I going now? So you are coming from, this is going to be high, and this is going to be low. So you're going to a lower temperature, that's automatically saying that you are going to a lower internal energy. Correct. Very good. All right, guys, you got it. So it's supposed to decrease. Okay, sort of get the feeling of what's happened in this business right here. Okay, so all the tools that we have learned start to come together and help you to determine the final answer. Part D, guys. Did heat enter or leave the gas from A to B? Now this is more serious. We practiced this last time using just like a table and stuff, but now it's more serious here. What should be the heat now? Leaves or enter. So it's just the question is, what's the sign of the Q? Is Q positive or negative? If Q is positive, means heat enter the gas. If Q is negative, means heat leaves the gas. What do you think? All right, so everything goes down to first law of thermodynamics first. Delta U equal to Q minus W. So the Q, heat, is the delta U plus W. Looks familiar? Very good, very good. Yeah, you got it. So the delta U is already negative. You just saw that because it's decreasing. So it's mean the delta U is negative. Okay, let me write it like this. So the delta U is negative. W, you already calculated there, is also negative. So definitely net, this is going to give you a negative Q. So at the end, you say heat leave the system. Cool, you are done.
Okay.
Wait. Okay, that's a very good comment here. Leaves mean less energy. What do you think? Like thermodynamics is like, make you guys crazy. Every time that heat leaves the system means less energy. Yes or no? It's not wrong or right. If you, it's the same thing as the question that I asked you guys. Remember, if I say, hey, I warm up the room, let's not, the room cannot be expanded. I warm up a gas. Does the gas get hotter? It's an incomplete information. So if you just only say from like, just like the general scenario, like, hey, if heat leave the system means less energy, you have to say, wait. What about the work? You guys got the feeling of what we are doing in this business round? You have to know everything first before you get your final answer. By just seeing that the heat leave the system, you forgot to look at the work. Remember that there are two ways that you can transact here. There are transactions method over here. Okay, so you have to check what happens to the W first before you can eventually arrive at your final answer in the delta U. Does that make sense? Yeah. So always, okay, take care of these two. So just heat leave the system, you only look at the Q. So you have to look at the W too. All right, so next question here. If one of the delta U or W is negative and another is positive, do we need to find the actual values? Yes, to be able to actually finally determine what is going to be the final answer. Correct. Yes. Very good. All right, but that's it. Answer your question. Yeah, about if the heat leaves mean less energy, the answer is it could be anything. because it depends on the work as well. Okay, it could be the same, it could be decreasing, or it could be increasing. You have to know Q and W first. Okay, I think you get the
Okay.
feeling now. All right, and I think by having these kind of questions, that you sort of like go in the right direction here. All right, so just keep asking. All right, as long as you ask, and then we get some corrections in terms of like how to use the first law of thermodynamics. You will understand more, understand better how this thing works. All right, next, guys, it will get better. Here, try again. All right, we have a couple chances to try today. I hope you're still having fun here. An ideal gas is taken from A to B, Now you see that it's an isovolumetric. There's a constant volume process as shown. During this process, 700 joules of heat is added and the pressure doubles. Oh, that's nice. So the information is already right there. So you know that the pressure at B is going to be 60 kilopascal. Okay, A, how much work is done by or on the gas, guys? Woohoo!
Okay.
No need. Okay, what about A? How much work is done, guys? Very good. Yeah, all right.
Okay.
Nice. Okay, you got it. Nice. B. What about how about this temperature of gas? From A to B. What do you think? Now start to get a feeling here. Part B, it seems like, oh, Ajahn, it not involved the thermodynamics just yet. You just want to compare the state A and the state B. Okay, so let's do B over T A equal to B over TB, shall we?
Okay.
And because you have constant volume, so that VA just disappear. And then you say that the pressure at B is twice as big as the pressure at A. So the temperature at B is supposed to be twice the temperature at A as well. Okay, so T at B is gonna be 2 times the temperature at A. Okay, all right. I did this problem already, and I think I made one big mistake right here, guys. So this one is my bad. All right. So I think I over inform you guys, and that makes things sort of incorrect. So can you just erase this part for me? Just forget about 700 joules of heat, because I mean, it's my bad. It has to pick one or the other. That's why I hate this thermodynamics part. When you decide the problem or when you decide the questions, you have to double check if everything's follow thermodynamics or not. And what I did over here is not. Having 700 joules of heat and double the pressure doesn't go together. It's against the law. That's my bad. All right, just showing you that that's how easily it is to make mistakes right here. It's just sometimes I just, hey, I want this heat to flow in and then pressure double, but once I calculate it, nope, doesn't work. All right, so stick with one. All right, you just have to pick one. So I picked pressure just double. So in that case, the temperature will double as well. And once again, just go back to our business of PV diagram treatments over here. Every time that you see this, PV diagram, just sort of have this isothermal line having sort of overlay on top of PV diagram all the time. I'm not sure is this good or bad, but it seems like it's very useful for me, and it seems like it's going to be useful for anyone who's doing maybe chemistry or whatever in the future, and then always have to refer to the PV diagram. It seems useful. Okay. All right. Now, so going from A to B is clearly can be seen that temperature must be rising because it's jumping from a lower isotherm to a higher one. So temperature is supposed to be higher, and we know exactly it's supposed to be double. Part C, guys. Now, cool. How does the internal energy of the gas at A compare to the internal of energy at B? Well, Ajahn, you already saw this. Temperature is double. So the internal energy of gas at A is supposed to be half, or I mean at B is supposed to be double as well. So it's easy to see right away that the internal energy at B is going to be twice the internal energy at A. Does it sound good? All right. And actually, if you want to know the change the delta U, which is U at B minus U at A, you can just do the calculation right away. U is always 3/2 nRT, correct? So it's going to be N 3/2 nRT at B minus 3/2 nRT at A. All right. And now, because you don't know the information about the temperature, but actually we can go away with nRT equal to PV all the time. Yeah, use equation of states. And you know the pressure, you know the volume. Oh, that is doable. I can pull 3/2 to the front and I take PB 60 kilopascal. Kilo. I turn it into Pascal over here. V at B is 0.05. Okay, let me omit the units here. Okay, and then I just subtract P at A is 30 kilo and same volume. There you go. And that's it. You are done.
Okay.
Okay, so you know exactly what should be the change of the internal energy during this process. And not only this is a constant volume process. The first law of thermodynamics says delta U equal to Q minus W. Okay, you're gonna write this down like crazy every time. Like, get sick of this. W is gone. So Q equal to delta U. So that means whatever delta U that you got here is going to be exactly the same as the Q as well. Okay. And no doubt, if you just look at this one, remember the 3/2 factor that we had before? It's always there because this is a constant volume process. Heat flow is 3/2 nR delta T. Everything just run, back and forth within this circle of first law of thermodynamics right here. Okay.
Okay.
Not bad. And I hope you see why I have to erase that 700 joules. Because once I punch the calculator, this number is not 700. So it's my bad. Okay. So I cannot. I have to give you correct information only. Stay within law of thermodynamics. It's so easy to make mistake here. All right, cool. Sounds fun so far. All right, guys, let's do one more, shall we? All right. So this is going to be a long one. Is it long? Oh, two more, sorry. Two more. All right. So let's do a quick one first. It starts to get more complicated over time. PV diagram shows a series of thermodynamics process. In the process A to B, 150 joules of heat is added to the system. All right, so let me write on the side right here, QA. Let me write AB right here, just save some space, right? So it's in QA to B, just write it as QAB. Okay, and that is 150 added. Don't forget the sign. So it's going to be positive 150 because you add it to the system. Now, in the process B to D, is 600 joule is added. So QBD is 600 positive joule. All right, that's a known information there. Find part A, the internal energy change in the process A to B. Just jumping from A to B, guys, just A to B. So part A, I want to figure out the delta U going from A to B, or that means just U at B minus U at A, right? That's what we want. Okay, delta U from A to B. Okay, how can we do this? First thing first, A to B is, what type of process is this? Well, Ajahn, it's a constant volume process. So easy thing right away is the W is definitely gone. So let me write WAB is just 0. Isn't that nice? And from the first law of thermodynamics, delta U equal to Q minus W. W is gone, so it's definitely equal to Q. But we already know the Q from A to B is just positive 150. Woohoo! And you are done.
Okay.
Isn't that fun? It's like 150 joules. So far, so good. All right, try again, part B. Now you want to figure out the internal energy change in the process A to B and then to D. All right, Bajan, that's no big deal. We have already taken care of what is going on from A to B, right? Delta U from A to B is 150 joule positive. So what we want to know is what is going on with the delta U from B to D. Right? Just do the next process right there. Okay. So what do you think is going to happen? So this is what we are trying to get to. Okay. Once again, from the first law of thermodynamics, delta U equal to Q minus W. Let me put BD on in all of this. Yeah. Okay. But one thing that we know right away, QBD is right here. It's already waiting for you. The first term is done. It's positive 600. Positive 600. That's already the first term. That's known right there from here, 600 joules. So what you have left to calculate is what about the work done from B to D? Yes. If you have that, subtract it out, you get the delta U that you want. What is going to be the work done from B to D? No. Work done from B to D is going to be the area under the curve right there. Here you go. Let me sort of draw that. Yeah, right? Just figure out the area under the curve from B to D. That will be your WBD. Okay, it's just a rectangular region. And then you go from B to D, you expanding. So I can say it right here, minus P delta V. We have done this like a million times now. Okay, it's just a rectangular region. And as you can see, here, let me write on the side over here. P at B, okay, right here, times delta V is going to be V at D minus V at B, right? V final minus V initial. So it's going to be 8 times 10 to the 4th times the volume change. You're going from 2 to 5. So the change is positive 3. So it's positive 3 times 10 to the negative 3. Let me omit the unit here, make it a little cleaner. So it's 240 joule and it's positive. And that's it. You can just throw this thing back in here. That's 240. It's this dude right here. Cool. Okay. So with that, then at the end, what you say is the delta U BD just from B to D is going to be 600. Subtract out the 240. So it's going to be 360 joules, still positive though. Yeah. You are done for part B. Cool. Yeah. All right. And that makes perfect sense because going from B to D, you still have increase in internal energy. Why? Because I think you're going to get sick of this already. Imagine isothermal line right there. Woo-hoo. Woo, right there. B, C might not be on the same isotherm, but okay. It looks so close. All right. But anyway, here, there you go. Right. It could be a different line for each one. It's so bad. Okay, let me just exaggerate it a little bit. Let's say I don't even know if which one is on top of which, but anyway. Okay, here we go. So you have your imaginary isotherm, right, lying around, but going from A to B, you go up in isotherm, and then from B to D, you go even higher lying isotherm. So at the end, you get positive delta U from A to B and positive delta U from B to D. What's going to be your final answer for this? Delta U A B D is just you taking this 150 joule and 360 add together. It's going to be delta U from A to B plus delta U from B to D. And that's going to be 510 joules. And you are done.
Okay.
Cool. All right. And this is once again the nice thing about the U. You can just go in pieces. It doesn't matter. Right? At the end, you know exactly what happened between A and the final point D, regardless of whatever point is going to stop by. So let's move on to part C, guys. This is going to be clearer. So when you look at part C, find the total heat added during process. Now, A, C, D. Now you want to go in a different path now. You want to go at the bottom path. You don't want to go up anymore. Okay, guys, if you can do this, I think you understand how to do thermodynamics now. Part C, they want to figure out heat. They want to figure out heat. So from the first law of thermodynamics, delta U equal to Q minus W. So the heat is going to be delta U plus W. You guys with me? Haven't done anything. Because now you want to travel from A to C to D. So the delta U that you want is going to be ACD plus WACD. So first good. Now, what do you know? บอกอาจารย์ WACD is going to be the same as a WABD change. You guys with me? The change in the U from A to C to D is not going to be anything different from A to B to D. Why? Remember, once again, let me confirm this. Energy. You start from here, you end up there, the top of my screen. Everyone knows the top of my screen is MGH. Down here, let me say we set that to 0. I can move up, it's MGH. I can go zigzag, zigzag. I got MGH. I can throw this mouse to you and you throw back and stop here. It's MGH. It doesn't matter. It's path independent. You start from the same point, you end at the same point. The change is going to be exactly the same no matter which path you take into your consideration. So that's why first term, you don't need to recalculate. The internal energy change from A to C to D is going to be exactly the same as that you just did A to B to D. So the first term is done. Okay. All right. So the heat is going to be, the first term is 510 joule positive. Keep it there. Okay. My J looks so bad. Just look like number 5. Okay, here we go. Okay, first term is down. Now, the only thing left for you is what about the work done from A to C to D, guys? Oh, that's just area under the curve. C to D is good. You get away with 0 work done. So the only area under the curve you have to figure out is just this. The smaller rectangle right there. Just this rectangle here. You want, this is WAC. And that's it. Plus, you know it's going to be positive work done because you expanding the gas. Okay. You just do the width times the height. The height is 3 times 10 to the 4th Pascal. The width is once again from 2 to 5. So it's 3 times 10 to the negative 3 cubic meter. And that's it, guys. You are done.
Okay.
Yeah, it's kind of fun, I think. I don't know. But at least it's not like crazily difficult in terms of the mathematical methods, right? You don't have any like crazy integral to do. You don't have any like vector decomposition. You don't have to do like, you know, I don't know, some free body diagram. No, it's purely like you're doing accounting right now. Right? Just you account for the transaction, right? What is going to be the transfer? Yeah, energy in, energy out. What is going to be the change in your energy balance? Yeah, it's kind of nice. Okay, all right. Maybe you don't feel the same thing as mine. Okay, guys, try one more. Last one. All right. This is a big one. We have like 4 questions, but I hope it's going to be a lot easier now. Okay, come along with me here. A graph in the figure shows PV diagram for 1 mole of ideal gas. Okay, find the pressure of the, or it's helium. Okay, oh, that's, I remember now. I forgot to put the name in the top. Okay, find the pressure of helium at point A. And from this one, they say that A and C, this is isothermal process. So that means I can, in my head, overlay an isothermal line here. That's good. All right. Okay, let's try part A. Part A is still okay, but John is just once again state of the gas. It's just comparing state of the gas between points. So PA over TA. Now you want to compare with what? You want to compare A to B, that's fine. A to C, that's also fine. Doesn't matter. Let's pick PCBC over TC, or like it could be PBVB over TB. That's your choice. Up to you.
Okay.
Okay. Okay, let me pick the first two then. The good thing about the first two is they are lying on this isotherm, the same isotherm, so temperature must be the same. Okay, so among these two, that means P times V must be fixed. So as you can see, the volume is 1/4 from A to C. The pressure must be compensated 4 times as well. So you know right away, this is going to be 8 Pascal times 10 to the 5th. Good. Got that one? All right. So that's it. So the pressure at A is going to be 8 times 10 to the 5th Pascal. Done. Move on. Part B. Find the temperature of this gas at point A, B, and C. Can you do that? Well, Ajahn, that's easy now. Because let's look at part A. If you want to get part A, pressure is known, volume is known, number of mole is known. So PAVA equal to nRT at A. You guys with me? Just use equation of state. So that means the temperature at A is going to be the pressure at A, 8 times 10 to the 5th. Volume at A, let me omit the unit. Everything is in SSI systems. That's kind of nice. 0.01 divided by the N, the number of mole, and R. Just leave R there. I mean, you can substitute R whenever you like, but let's just make it clean. And that's it. So the temperature at A is going to be, I think this is easy to work out, 8,000 over R Kelvin. All right. And whatever this temperature is going to be the temperature at C as well, because they are on the same temperature. They are an isothermal process from between A and C. All right, 2's down. What about B? Well, Ajahn, temperature at B is fine, because once again, you can just go back and look at the here. One of these 3, I mean 2. You can pick 2 out of these 3. Just compare. Okay, so probably I can do comparing between A and B, same pressure. So from here, what I can do is, Ajahn, A to B, the volume increased 4 times. So A to B, the temperature must be 4 times as well. Why not? Because we have done that already. So once again, in your head, goes like, oops, sorry. In your head, go like this. There. So going from A to B, you must rise in temperature for sure. How many times? Volume expand 4 times, temperature must expand 4 times as well. Cool. All right, so that's it. So temperature at B is going to be 4 times temperature at A. So it's going to be 32,000 over R. You are done for part B.
Okay.
Now try part C. How much heat entered or left the gas during each segment from A to B, B to C, and C back to A? And here comes our good friends, the expression we have already worked through. And this is where we can benefit from that. Let's start from B to C first, guys. QAB. Now you start to get the feeling. AB is very good.
Okay.
Isovolumetric, right? I'm sorry, isobaric, right? A to B is just a constant pressure process. So it's going to be 5/2 nR delta T. Isn't that cool?
Okay.
Yeah, remember this? Yeah, this. Go back. Here. Isobaric process. We can jump right ahead into calculating of the Q equal to N C sub P delta T, and C sub P is 5/2 R. But for those of you thatบอกอาจารย์, I don't want to memorize this, that's fine. You can go quickly by just say from the first law of thermodynamics, Q is just delta U plus W. Delta U is always 3/2 nR delta T. W is P delta V in the constant pressure process. It's just a rectangle. But P delta V, you can use equation of states. So this one give you extra nR delta T. So you add up into 5/2 anyway. See? So if you don't want to memorize any formula, you can start from the first law of thermodynamics. You're going to get the same results anyway. Okay. But once you're comfortable working through this way, yeah, the heat from A to B is going to be 5/2 N is 1, R is R. Temperature change from A to B. So this is going to be T sub B minus T sub A. You already knew the temperature in all points. Put it in. 22,000 over R. That's temperature at B. Subtract temperature at A is 8,000 over R. Keeping R there is nice in the sense that now R cancel. And the good thing that you get here is just what? It's number calculation here. 24, 12, 60. There you go. Joule, and you are done.
Okay.
Okay. Not bad. Not bad. I hope it's very doable. Okay. So now you start to see what can be done next. QBC. Now it's going to be cool because BC is the constant volume process. You know it's going to be 3/2 NR delta T. In your head, it's the same as a delta U as well. Because when you have a constant volume, there's no work done, heat is going to go into the change in the internal energy. And for the monatomic gas, it's 3/2 NR delta T. And you are done. 3/2, N is 1, R is R. Delta T is going to be T final minus T initial. So it's going to be T at C minus T at B. Nice. Temperature at C is 8,000 over R. Temperature at B is 32,000 over R. All right, R cancel again. Bam, bam, bam. And then what you get at the end is going to be negative, guys. Be careful here. Okay.
Okay.
Negative. And then work through the numbers a little bit. It's going to be what? 36,000 joule. You are done.
Okay.
For the second segment over here. Cool. Am I doing the right number here? I think so. 1236. Okay. All right. Cool. So far so good. Now let's pause here a bit. Just make sure that you see what I'm doing over here. I'm sorry, I'm running a little bit over time here. All right. So what you have here is QAB is positive. For what I'm having over here is means during AB there's a heat flow in because you have a positive heat. Okay. So that's what this one is, heat. But then when you move on to B to C, heat is out, is negative. I can draw the arrow over here. Oh, let me change the color here. There's a heat flow out. Q, B, C. That's right there. That's a Q. Okay, you start to see the connections now. And then you have one more left to do is what about just C back to A? Oh, all right. C back to A is fine. Q, C to A is going to be, what is that? Very good, because it's an isothermal process. So that means it's going to be equal to W and it's going to be equal to nRT log V final over V initial. See that? So we utilize everything that we have learned today and just plug it in. So because right now you can see that N is known, R is known, T is known, log of V change is also known, but because from C back to A, you're compressing the gas down. Log of negative number, log of the number less than 1 going to give you a negative number. So that means going from C back to A, you're going to get a negative number right here. And that will give you heat leave the system, QCA. And that's heat right there. Cool. All right. So that's what I'm trying to say that, hey, under the first law of thermodynamics, you're just going back and forth between these expressions. And then among these three, delta U, Q, W, you are able to calculate anything you like. Okay. Now, final question before we end today's lecture, guys. Part D. By how much did the internal energy of the gas change during each segment? This is like go back in question because this one is just easier to calculate. Delta U AB is always 3/2 NR T final minus T initial. You are done. Make sense?
Okay.
Yeah. All right. delta U B C is always 3F NR T final minus T initial. No problem.
Okay.
And delta UCA, you don't even have to think, is definitely 0.
Okay.
Yeah. So delta U is fixed with the expression of 3/2 in RT. So that's why asking the internal energy change is actually even easier than the heat. And just to be proper, I actually, or in general, people will ask for the internal energy first and then asking about the heat at the end, because it seems like heat is the only one that seems to be more complicated to calculate. All right. However, well, it came this order, so that's okay. You already worked through everything. So go back to the delta U here. It's going to be easy. And that is done. Okay, guys?
Okay.
Isn't that fun? All right. So next time we'll do more. Don't worry. The reason that we focus so much on heat, because next time we are going to make use of this heat, that exchange and everything, and we're going to build an engine that can operate between hot and cold portion of the environment and stuff, and hopefully we can extract some useful energy and make the engine perform for us, lift the weight, turn the motor, turn things, doing useful thing. All right, and next time I'm going to show you the best engine in the universe that even Tony Stark, Thanos, or whoever Eternal, or maybe Eternal can do it. As long as they use our physics right here, they're not going to be able to make a better heat engine than what we are about to discuss next time. Okay, guys? All right, that is it for today.
Okay.
I'll see you guys next week. Thank you.